Okay, welcome everybody to the Virtual Time Series seminar. Our speaker today is Bertille Antoine, and she's joined with our guest panelist, Daniel Lewis. The paper is Efficient Two-Sample Instrument Variable Estimators with Change Points and Near Weak Identification. It's a pleasure to have you both. Thank you both for accepting our invitation. The speaker will be taking questions throughout, so please, if you have a question, just unmute and ask your question. Bertille, the floor is yours.
Thank you, Majid, and thank you everyone for being here. It's a great pleasure to be invited to speak at the VTSS. So this is a joint work with Ottilia Baldia and Nicolo Zaccaria. Both of them are at Tilburg, and Nicolo is a PhD student on the market this year, but more in the macro than the time series. So we are working on efficient two-sample IV estimators, and then we have change points and we have near-weak identification. So in this project, we are interested in developing estimation and inference in linear IV models. And as the title suggests, our linear IV models have two features. The first one is that the parameters may change abruptly in the sample. And we are talking here about changes of the slope parameters, as well as changes in the parameters that are governing second moment, so variances, as well as relationship between instruments and endogenous variables. And the second feature is that these instruments may not be very strong. So in this framework, our main insight is that we are proposing to use stability in the parts of the models that are not changing as an additional source of information. And traditionally, you can think about when there is an abrupt change in part of the model, what has been done in many applied work is to split the sample and then to conduct estimation and inference in both parts separately. And so implicitly, you are kind of assuming or relying on the fact that everything is changing at the same time. And what we are proposing to do is to realize that, in fact, in many cases, this is only a part of the model that is changing while many other features are remaining stable. And what that means is that we can gain some efficiency by relying on those stability conditions. And that can be quite important in the type of examples that we have in mind, in the macro type examples, where the samples are to begin with relatively small. And so you can imagine that if you have to split a small sample, then it becomes even more small. And so things become more complicated. And then another feature of the macro examples that we have in mind is that instrument may not be very informative. And so once again, when you split the sample, then you may face additional constraint on the strength of the instrument that are appearing even more weak than they really are in practice. And so technically speaking, what we are doing to use stability as an additional source of information is to add moment restrictions. I will be a little bit more explicit about what or how we are doing that. And then these additional restrictions are going to bring us some efficiency, basically. And in this project, we have two sets of contributions, both methodological and empirical. So let me be a little bit more explicit about the type of contributions that we have. So first of all, in terms of estimation, we are going to show that our stability is effectively bringing us more efficiency. And so when we compare our estimators to traditional ones like split sample or even some other estimators that are available in the literature, we can show theoretically that they are more efficient. So in other words, this stability condition that we bring in is not redundant and bring new information that is translated in terms of increased efficiency. And this increased efficiency is even documented when we have near-weak identification. The second part is about the structural breaks or the abrupt changes. And here we are going to develop tests to detect the changes and also to estimate those change points. And we are going to develop these tests that are, in fact, extensions of existing tests. In many cases, what we propose is following the line of what has been done in the past in a sub-world test or some other type of world test. And what we are able to do is to derive the limiting distributions under the null and under the alternatives. So characterize the power properties and show that the power is non-trivial even when we are facing weaker identification, even when identification may be changing throughout the sample. So those are the main contributions on the theoretical side or methodological side. And then for the empirical contribution, we have a long list of Monte Carlo experiments. I will not be presenting them due to time constraint, but you can trust me that things are working in simulations exactly as we expect. One thing that I want to mention, again, because I won't have too much time to talk about it, is the fact that you may, so in a GMM framework, when you add additional moments, you might wonder if you might be experiencing something like a bias variance trade-off when you add more moments, especially in finite sample. But in all the Monte Carlo experiments that we have looked at, we didn't really see that at all. In fact, our estimator was consistently the one with a smaller bias and more efficient as well. Again, compared to the estimators that we considered as well. What I will have time to talk about is the application. We are estimating an open economy in New Keynesian Phillips curve with American data. And what we find is a strong support for an incomplete pass-through and important time variation in a relationship between inflation and exchange rate pass-through. And that has important implication for macro monetary policy and related topics. So hopefully I will have time to talk about all of that. So let me give you an outline. I will start by introducing our framework and motivation. Specifically, I will be talking about 3 motivating examples, 2 time series and 1 cross-sectional. Obviously, in this seminar, everyone is very much in favor of time series, so I don't have to convince you of how important it is. Nonetheless, my co-author Bertille brought a very interesting example to mind that kind of broadened the application or the applicability of our estimator, and I want to take a few minutes to talk about that. I will talk about literature very quickly, and then jump into the main theoretical results. I will focus on a simplified framework just to give you the intuition of how things are working and why they are working. Mention briefly all the extra results and extensions that are available in the paper that I don't have too much time to talk about, and then spend some time on the application. All right, so as I mentioned, our framework is really the standard linear IV regression model. So we have a univariate dependent variable that I call little y. And then I have 2 sets of regressors, included exogenous variables that are Z1, and then endogenous variable X's. And of course, to handle the endogeneity of X, I have access to instrument, and all these instruments are collected in big Z, collecting the new instrument as well as the exogenous variables that are common to both equations. We are extending this standard model in 3 directions. We want the parameters of interest, or the slope parameters, the theta z and the theta x. We want to allow them to change abruptly across subsamples. We also want to allow for second moments to change abruptly as well. So that means the variance of the moment, the second moments of my instrument, and of the structural errors U. And the third thing is that our instrument may not be strong. We are not considering the limit case where they are truly weak, but we will consider intermediate cases where they are near weak, and we will follow the usual path to model that, and I will come to that in a moment. So the simplified framework that I want to consider in this talk is to consider the situation where the reduced form, so my first stage, if you wish, is not changing, it remains stable, and the structural equation is not, so it is changing, and in fact, it is changing abruptly at one given point in time. So before I move forward, I want to, maybe you are thinking about, well, why is this situation? How come the structural equation is changing, but the reduced form is remaining stable? And so before getting into too many details, I want to bring you a couple of motivating examples where I want to highlight situations where we believe this is credible to have this situation, a stable reduced form, and a structural form that is not stable. So we have 2 macro examples, as I mentioned before. The New Keynesian-Phillips curves will happen to be our empirical application in the paper. I will also talk about another popular example based on local projections. So let me start with the New Keynesian-Phillips curve. So this is a model that is focusing on the dynamics of inflation based on current inflation predictions and unemployment gap. And both these variables are typically endogenous, and you use instruments that are built on lags of these observed variables to handle endogeneity. So this is a well-known example that has been studied quite a bit, and there is strong evidence suggesting that parameters linking inflation and unemployment gap change over time. But of course, there is no reason to believe that the dynamics of inflation expectations or unemployment gap would change at the exact same time as the unemployment gap parameter does, right? So this would be a situation where over a period of time, the reduced form would be relatively stable, whereas the structural form would experience these abrupt changes. Another example where we might have a similar situation is based on local projection. And here I want to build on a recent paper by Remy and Zuberi. And in this paper, they are interested in whether government spending multipliers are different depending on whether interest rates are at the zero lower bound or not. And obviously, until very recently, interest rates were very close to the zero lower bound for quite some time, since probably 2008. And so what that means is that you could write this as a regression of output at different horizons on government spending before and after 2008. Government spending is endogenous, and you would use some kind of external instruments. This is exactly the study that Remy and Zuberi did, and they use the Blanchard and Perotti shock constructed as a measure to measure an unexpected discretionary change in fiscal policy over the sample. So once again, this is a situation where it's not really clear why the relationship of the unexpected component of the fiscal policy with fiscal policy itself should change exactly at the same time as interest rates hit the lower bound, the zero lower bound, right? So this is a situation where you would have that case where the reduced form would be relatively stable, and then you would experience a change in your main equation or structural equation. The last example that I want to talk about is, once again, kind of switching gear a little bit. This is a micro-based example, and broadening kind of the scope of our understanding in terms of abrupt changes. And here, this is based on a two-sample type of estimation. So in this example, it's a very classical example in applied micro. You're interested in the effect of age at school entry on educational attainment. And because parents may enroll children earlier, the age at school entry is endogenous, right? So this is the classic study of Angris, 1992, and they used the quarter of birth dummies as instruments. So quarter of birth and age at school entry come from one sample of individuals. Quarter of birth and educational attainment come from another sample. So this is why it's called the two-sample IV estimation. And the way it works is that the first stage is estimated in one sample and plugged into the IV estimator of the second sample. So in other words, it is as if the first stage is assumed to be common to the two subpopulations, but of course, it's different for the second stage. And so if we observe the age at school entry and educational attainment in both samples, which is likely the case when we have access to new administrative data, then the relationship between educational attainment and age at school entry may be heterogeneous across the two samples. And accordingly, the parameter of interest may change across these two samples, right? So this is some kind of, broadly speaking, group heterogeneity here because we have two samples. But more broadly, you could also think about group heterogeneity where subgroups of your population may be facing different slope parameters, while the underlying relationship or the intake for treatment may not be changing. All right, so I think I have done hopefully enough to convince you that it makes sense to look at a situation where we have a stable first stage and a second stage that would be abruptly changing. So let me briefly talk about related literature before moving on. So there is a rich literature that is talking about linear IV model in presence of abrupt changes, or in presence of some kind of weaker identification. But not too many papers are talking about both issues happening at the same time. Of course, there are two exceptions, one being my my previous paper with Bertille, and another one a little bit earlier published in Econometrica by Magnussen and Mavroidis. And so they, both these papers consider weaker identification in presence of structural changes. The difference is that both assume that the structural parameters do not change. So it's more like the first stage is changing and the second stage remains stable. We are kind of flipping things over, allowing for the first stage to be stable while the second stage is changing. And also in our broader scope, we are actually allowing both equations to change, but possibly at different times. So you have periods of time where one equation is changing while the other is not, and vice versa, okay? So to simplify the talk here, I'm going to focus on the simplest of the framework. That is the most different from previous work. And that will be enough for me to give you the intuition of how we are using stability and why it is providing new information that is not redundant and that leads to improved efficiency. So let me go right into that. So we have our structural or second stage equation. And as I mentioned, there is one change happening at T naught. And for the sake of this first part, let me assume that you know T naught. So one known break here at T naught, and the slope parameters are changing. Nothing else is changing. Now, you have a reduced form that links your endogenous variable with your instruments. And because we want to allow for weaker identification, we use the usual way to model weak identification introduced by, Steiger and Stock quite some time ago, where the parameter of your first stage is drifting to 0 at rate alpha, which is, not too fast, so that it's not truly weak. We are not allowing for the boundary 1/2 to be included, but it can be anything between strong, where alpha would be 0 and there is no drifting to 0, up until what has been now referred to as near weak or near strong, depending on what kind of team you are on. All right, so in this context, as I mentioned, our main goal is to, of course, provide reliable and efficient inference on the slope parameters, theta naught, before and after the breakpoint T naught. So what is available in this situation? There are two, families of estimation procedures. One is a split sample that was introduced by Andrews. And as the name suggests, you are breaking everything into two subsamples that are, for the most part, completely disconnected. So are using the pre-break subsample, and you are using moments based on your instrument before and your parameters before the break theta 1. You can provide your theta 1 hat, which is basically a normal GMM or a simple GMM when you focus only on the pre-break subsample. And then you can do exactly the same thing on the post-break subsample, and then you will have your theta 2 hat as a normal quote-unquote GMM estimator, right? So this is the split sample. Everything is completely separate between the two subsamples. Recently, Bertille and co-authored proposed what I like to call a hybrid two-stage least square. And this is like a two-sample two-stage least square, so TS2SLS. And it is hybrid because it is borrowing a little bit from the split sample and borrowing from the two-sample literature. So the split sample part is that you are going to get your two-stage least square from the split sample. After plugging it y hat, which is the estimator that you obtain on the first stage, but this time, this is the whole first stage. So you are not cutting your first stage into pre and post break. You're using the full sample in order to get your y hat, your predicted endogenous variables here, and then you plug them in the split sample. So that's why I call it hybrid. It's full sample for the first stage, so you are using, to some extent, the stability, but it is split sample in the second stage where you are doing a little bit of this hybrid approach, okay? Oops, sorry. So what is our idea? Our idea is to go one step further than the hybrid 2SLS approach. And what we want to do is we want to use of course, the same moments as the split sample, because these are the moments that are going to give us identification of both slope parameters, θ1 and θ2. But instead of doing this plug-in 2SLS full sample approach, we actually want to take the stability of the first stage more seriously. And what that means is that we are going to not use the full sample moment over the entire sample. We are going to use split sample moment of the first stage, but notice that the pi parameter, which is the parameter that is the slope parameter in my first stage, is the same. So this is how I am imposing my stability. So why do I need two sets of moments? So effectively, I am now doubling the set of moments from the first stage, whereas the two sample 2SLS was using the full set of moments. Okay. This comes from a literature in GMM, early literature, which was talking about nuisance parameters and redundancy of information. And so in some ways, you can see the pi parameter as being a nuisance parameter when it comes to the estimation of the thetas. And so if you just identify that pi, there is no way you are generating new information that could be used to improve upon your estimation of the thetas. Now, by doubling the number of moments, it turns out that you are now over-identifying the pi parameter, and providing this information is useful in the sense of non-redundant to estimate the theta parameter, you can actually show that you are going to get a more efficient estimator for the θ1 and the θ2. And that's exactly the insight as to why things are working. So these extra moments now over-identify pi, and what we do end up showing with matrix algebra and the usual tools is that this information is not redundant. So effectively, we are able to show more efficiency. So let me talk a little bit about the asymptotics in this situation. So first of all, we have general regularity conditions that are... Oh, yes, sorry.
Having a break at the beginning or at the end could cause any issue, or... I mean, I think this is a classical problem in structural break, right?
Yes, absolutely. So in that case, we don't have anything new to talk about in that sense when the T naught is very close to the beginning or very close to the end. We are facing the same issues as classic literature in that situation.
Thank
so
you.
Yes, absolutely. Thank you for clarifying that. Any other, I guess, I forgot to mention, to ask if there was any question or comment at this point. All right. Okay, so let me move to the asymptotics then. So we do have general regularity conditions, nothing special about them. We allow for general patterns of weak dependence, including autocorrelated errors and so on and so forth. In that situation, the three estimators that I mentioned, so the split sample, the hybrid or two sample 2SLS, and our new estimator, two sample GMM, all of them are consistent at the same rate. And the rate depends, of course, on whether you are estimating the slope parameter of an exogenous variable, in which case you get the standard square root of the sample size rate, or whether you are estimating the slope of an endogenous regressor. In that case, the rate will be affected by the degree of weakness. And so the rate will be slower depending on how weak the instrument is. So this is all very classical result based on some of the work that I have done with Eric, and there is no difference in that situation, the presence of the break or not. So all these estimators are consistent at the same rate. They are asymptotically normally distributed. Now, of course, the main question is about efficiency, and effectively speaking, whether these double number of moments that we are using from the first stage is going to provide relevant information for the estimation of the slope parameters. Okay. And there is a older literature on the redundancy of additional moments, and there is a lot of insights from the paper by Ann and Schmidt, as well as Borschke and Schmidt, all of them under strong identifications. I've done some work recently with Eric where we revisit the redundancy of additional moments when we have weaker identification. And basically, what we are able to show is that our two-sample GMM estimator is always more efficient than the split-sample GMM. And we have actually a formula that links these two asymptotic variants. And because we are able to show that we have this G prime G in here, that means that when comes the time to estimate these asymptotic variants, we can always guarantee that in sample, we will preserve the efficiency of that two-sample GMM. Now, when it comes to, and efficiency is preserved under conditional homoscedasticity as well as linearity of the second moment. Now, we also have condition to ensure strict efficiency, obviously, whenever this matrix is positive definite, and that translates into some high-level condition to guarantee that. Now, the second part is how do you compare the two-sample GMM and the two-sample 2SLS? This is actually not obvious at all. One of the reasons being that the two-sample 2SLS is that hybrid approach. It is not a special case, as one author picked about 2SLS as being a special case of GMM. Because of this hybrid nature of two-sample 2SLS, it's not a special case of our two-sample GMM. So the direct comparison of the asymptotic variance is not obvious at all. In our simulation, two-sample GMM tends to be coming on top for a large number of Monte Carlo experiments, but that's all we can say. We also have one special case of interest where we are able to prove that two-sample GMM is always more efficient. And this is the situation where you have only one endogenous regressor and no exogenous regressors. So you may think that actually this is an important enough special case that at least gives us some comfort that at least in that special situation, we are able to show that.
So just a quick question here, and this is just more kind of out of interest than kind of suggesting that it would provide an improvement in any way, because it almost certainly wouldn't. But is there a middle ground that you could develop here? So kind of along the lines of two-stage GMM, well, somewhere between two-stage 2SLS and two-stage GMM, where you're going to have the kind of GMM weighting approach that you'd associate, that you associate with these sorts of estimators, but without the over identification that you're offering. So I'd be curious how that would look efficiency-wise, right? Because you could imagine replacing two-stage least squares with efficient GMM using your instruments without introducing the extra over-identifying moments.
Oh, I see. So it'd be a different kind of hybrid.
Exactly.
Right.
I think it would be helpful to understand perhaps, if there are efficiency results between that sort of estimator and your estimator, because that would really highlight maybe where the efficiency gains are coming from that you're describing here.
Okay. We haven't considered that, but that is an interesting idea to gain some more, as you suggest, to gain some more insight as to where the efficiency gains are coming from. I guess a long time I've been a GMM girl, so I have studied moments and redundancy of moments and things like that. And the insight that I got from that early literature, that mid to late 90s literature, is really that when you have quote unquote a nuisance parameter, so not your main parameter of interest, but another parameter that is linking variables that enter the other part of your moment, as long as you have some kind of correlation between them, and as long as you are over-identifying that, the math works to show that this is going to be useful information, right? If it was completely independent, then no matter how much over-identification you would have, it would not translate into the estimation of the parameters you care about, right? So you need two channels, you need some kind of a correlation, but you also need that over-identification so that you have some leftover or extra degrees of freedom to kind of build on. But what you're suggesting is an interesting idea, so thank you.
So I think, of course it would have to be an over-identified, IB problem for this to have any sort of traction, but kind of in that over-identified case, just, I think you can get some improvements without the experiments.
Yes, thank you. All right. Okay, so a few additional results, keeping an eye on time here. So again, I focused here on the most simple framework where we had one known break in the second stage and then no break in the first stage. Of course, one of the extensions that is important for us to consider is the presence of an unknown breakpoint. And so unknown breakpoint, the break is there, but you don't know where. So we have an estimator for that. And the kind of true, maybe more realistic situation where you don't know if there is a break. So we have also a test to detect whether there is a break or not. And then we have extension to presence of a common break. So that would be one additional break, and you are trying to see whether this break is common to both equations, as well as extension to the presence of multiple breaks. So let me talk a little bit about the estimation. So the estimation is in many ways classic in the sense that you are going to consider the total sum of square residuals, and you are going to look at every possible candidate break within acceptable range to get sufficiently reliable estimation on each subsample. So as Abderrahim was mentioning earlier, we don't really have anything new to say about what happens when the break is really close to the beginning or the end of that subsample. This is an extension of some of the work that Ottilia has done with co-authors. And we are able to show that the estimated break fraction in this situation is consistent at a rate that will be affected by the degree of weakness. Now, in terms of detection, we are building on, once again, previous work of Ottilia and proposing the sub-wall test and showing that it delivers power. We are studying, so it is consistent. We also study its power properties. And what is interesting maybe to mention is that the power properties depend on whether there are exogenous regressors or not. Maybe not surprising for those of you who are familiar with the framework. when they are exogenous regressor, you get the fastest rate of divergence, T, and then when you do not have that, the rate of divergence depends on the identification strength, and it's a slower rate. Now, interesting to mention that the implicit change fraction estimator may not be consistent. Consistency requires maintaining an additional assumption about the homogeneity of the second moment. And that's something to keep in mind, maybe. All right. Detecting the common break. This is done through a wall test in a classical sense. And it is much more simple than the subwall test that I just mentioned. Reason being that you are able to compute directly the statistic at the estimated change point coming from the first stage. And so that simplifies the math quite a bit. Under the null, you will converge to chi-square p, p being the number of unknown parameters. And then under the alternative, it diverges. And once again, you have the different rate of divergence depending on whether you have exogenous regressors or not. All right. So at the end of the day, we propose a 3-step procedures that is comprehensive. First, focusing on the reduced form, detecting and estimating the breaks in that reduced form. Then you consider each subsample where the reduced form is stable, and you ask yourself whether they are breaks in a structural equation, detect them and estimate them. And then you study the whole system, possibly checking whether some of the breaks are common, and then finally estimating the parameters of interest based on those estimated breaks. All right, so in the last 15-20 minutes that I have left, I would like to talk about our main application, which is focusing on the estimation of the US hybrid NKPC in an open economy. So the New Keynesian-Phillips curve is actually quite well known and estimated to model the dynamics of the inflation process. Here we are focusing in its open economy, and what that means is that it's going to relate inflation to movements in the business cycle, as well as expected future exchange rate changes. Our hybrid NKPC looks like this. We have pi t, our dependent variable, which is inflation, which is measured as a CPI inflation. It is modeled as a linear function of expected inflation, first and second lag of inflation itself, and then two drivers, if you wish, UT, the unemployment rate measured as the output gap, as well as psi t, which is the pass-through rate. So that is the difference between real exchange rate and terms of trade. It's important to understand how these different slope parameters relate to each other and what would be important channel for possible monetary policy and its effectiveness. So in our estimation exercise, we have collected a sample of 440 monthly observations from the 83 until 2020. Two of our explanatory variables are endogenous, the expected inflation as well as the unemployment rate, and we are going to use lags of observed variables, first lag of observed variables, as instruments.
Sorry, Bertille, just a quick question. So where did you get the specification for this NKPC?
This hybrid NKPC?
Yeah.
I believe we borrowed it from a recent paper by Abbas. the name of the outlet escaped me at the moment, but I can search for it and let you know.
Okay, so I'm curious why, for example, not, lags of unemployment or lags of the pass-through, why not?
Oh, so you mean just the lag of inflation and no other lags?
Mhm.
I guess the specification was I guess I don't have a good explanation for that. I guess our
Yeah,
methodology
just curious,
allows
sorry.
for, sorry. But I will, maybe Ottilia will know more. I think she is in attendance and maybe she can answer that. But I should know that. Thank you. All right. Sorry, so just a few pictures to show you what these series look like. So top left here, I have inflation in blue and inflation expectations in red. Then we have unemployment rate, top right, and then bottom left, real exchange rate and terms of trade, bottom right here. So probably, yes, this is, it is what it is. All right, so how does our empirical strategy work? So we first focus on each reduced form. So we have two reduced forms here because we have two endogenous variables, so the expected inflation and the unemployment rate. So the first step is to study each of them separately and detect and estimate the breaks, possibly look for common breaks between these two equations. Then the second step is focus on the parts where both reduced forms are stable, and then ask yourself whether the corresponding equation for our structural equation, whether there are any breaks happening in there. Okay? And then once you have your estimated breakpoints, then you can estimate the three competitors that we are considering, the two sample GMM, so that is our estimator, the split sample GMM, and then the hybrid two sample 2 SLS. So the period that I'm going to focus on today is from 83 September until 2001 September. So this is the period where both reduced forms are stable. And when we use our new test to detect whether there are changes in the structural equation, we find one change at 92 April. So I present, there are a lot of numbers here. So on the far right, you have result obtained by a standard GMM that ignores the break in the structural equation. Okay, so one thing maybe that I did not insist on too much is that because we propose a new test to detect structural breaks in the main equation that is robust to various different things, including weaker identification and so on and so forth, this break would have been missed by many other methods, right? And so if you miss it, this is the kind of result that you get. So you do see that the lags of inflation, gamma 1, gamma 2, get some, traction, but the main parameters, kappa psi and gamma f and kappa u, there is not much action here, especially the kappa u, the unemployment channel. Now, the two left panels here are the estimation results obtained by these three competitive methods: two sample GMM, two sample 2 SLS, and split sample GMM. Ours is in shaded gray. And what we can notice is that there are significant changes between what you get for the first subsample and what you get with the second subsample. So first and foremost, if you ignore those breaks, the information you get from the full sample GMM is very unreliable. As you would expect, when the breaks are ignored, the message is kind of wrong. So that's, I guess, low-level thing. The second level is that in terms of estimates between the three different methods, the estimates tend to be close to each other. So once we have detected and estimated the breaks, the three possibilities that you have access to get those slope parameters in the main equation, they deliver estimates that are really close to each other. And of course, this is what you expect because they're all converging to the same thing at the same rate, so on and so forth. Where do we see differences is in the efficiency, which come through standard errors and how significant the different estimates are from each subsample. So first and foremost, as predicted by our asymptotic theory, split sample gets standard errors that are much larger than those obtained by two-sample GMM. The comparison between the two-sample GMM and the two-sample 2SLS is less clear. In general, you have situations where the estimates and their standard errors can be quite close to each other, but there are some other situations where it makes a difference, and two-sample GMM is much more precise than what you get for two-sample 2SLS. For example, here, the estimate of kappa U, the slope of unemployment, the standard error is much smaller with two-sample GMM than it is with two-sample 2SLS. Same thing here with the slope of the pass-through, kappa psi, much smaller standard errors. But again, we don't have, especially in this situation where we have multiple endogenous variables, we don't have asymptotic theory to say that this is, consistent with our results, but this is just, I guess, empirical evidence in this particular situation.
So I have more of maybe an empirical question, kind of trying to understand what's going on here.
Yes.
In that, we talk about the flattening of the Phillips curve over time, and it seems like you've almost got kind of a steepening of the Phillips curve in this set of results. So I know much less about these Phillips curves with exchange, augmented with exchange rates, trying to figure out these sorts of pass-throughs. I'm curious if this is more kind of a typical result in this kind of expanded Phillips curve literature, or is this a little bit of a puzzle to you that you've got a steepening over time of the Phillips curve with respect to unemployment?
Well, I would say that two things. First thing would be that to some extent, if you hadn't been able to detect your break, then you have that kind of flatness. Especially with respect to unemployment, and here to some extent with respect to the pass-through, right? So in that sense, our results are somewhat consistent with what you would have expected. Now, the time variation that we observed between pre-1992 and post-1992, I'm no macro expert, but it is definitely striking how the estimate change from one sample to the next. And also the fact that in some cases they are completely, it's not like they are changing and we can still not reject that they are the same. In some of those cases, they are very different and significantly different. And I'm not really sure what to make of this in terms of, whether this is completely at odds with what macroeconomists would expect. Honestly, I don't know. What I do say is that we have important message in terms of the pass-through, right? So this is significant throughout, and that's a result that is new. And the second thing is that the magnitude of the pass-through is also comparable to that of unemployment, at least for part of our sample. And so I think that this is something to pay attention to, whether we have paid enough attention to really, dig deep into understanding that or where it's coming from. I have to admit that we haven't done that. Yes. I guess I have just a few minutes. Yeah, so I guess key insight is that there is important time variation, and ignoring it is going to be heavily misleading in terms of what you think is happening versus what should happen if you really take into account this time variation seriously. And we have provided some new tools to do that, even with reasonable, macro sample sizes. Here we have approximately 100 observations, and our estimates are fairly precise. We are also using monthly observations, which may be different from some of the more mainstream macro empirical analysis that are using quarterly data. But of course, we do need a few more observations to be able to do what we are doing. So there's no free lunch here, but I guess it is fair to mention it. All right, so let me just conclude. So in this paper, we are focusing on the linear regression model with instruments. Our model allows for abrupt changes in the structural parameters in the second moment of the GGP, allows for near-weak identification. And what we provide is a comprehensive procedure to allow you to detect reliably changes in the parameters of the reduced form, changes in the parameters of the structural equation, and provide you with new estimators that are more efficient, because I guess as a shortcut for where the efficiency gains are coming from, they are coming from exploiting additional information in the form of stability restrictions. Again, intuitively, it's not because one part of the model is changing at a given point on time that everything else is changing. And so being able to use stability in, I guess, a creative way to ensure that the information is not redundant, to creating this over-identification, I guess, is our trick to be able to make this feasible. And then in terms of applications, we are estimating New Keynesian price in an open economy with American data. And our inference strategy definitely makes a difference in terms of recommendation for effective monetary policy. We do provide more precise estimates of the key parameters, and we provide tools to detect a break that would go otherwise unnoticed, and due to that would lead to really misleading estimates of these key parameters. So I will stop here. Thank you.
Well, thank you very much, Bertille, and thanks also to our guest panelist. I will stop the recording now, and then we can move to the question and answer.